Hello and welcome to the Toronto Geometry Colloquium. This is a weekly web series all about geometry processing.
This colloquium aims at promoting young researchers and researchers from traditionally underrepresented communities.
And every week, we will have an opener talking about their cutting-edge research for 10 minutes, followed by the headliner giving us a keynote presentation.
So this week we have two great speakers. Our opener, Ruojin Cai, is going to talk about learning gradient field for shape generation. And our headliner, Lingjie Liu, is going to talk about neural representation and neural rendering of 3D real world scene. If you have any questions, please leave comments in the YouTube chat or our Discord channel in order to curate a good Q&A session at the end. So first, it is my pleasure to introduce our opener, Ruojin Cai. So she is a talented PhD student at Cornell University, advised by Professor Barak Harihan and Professor Noah Snavely. She received her bachelor degree from Tsinghua University in China, advised by Professor Lu Jingwen and Professor Zhou Jie. After that, she spent a wonderful summer at Cornell University working with Professor Kilian Weinberger and Professor Zhou Jie. Her research interests lie in the field of 3D-related computer vision and machine learning. And the paper she's going to present today proposes a novel technique to generate shapes from point cloud data, which reaches state-of-the-art performance for point cloud auto-encoding and generation, while also allowing for extraction of a high-quality implicit surface. So without further ado, we will give the stage to Ruojin.
Thanks for the introduction. And let me share my screen. Today I would like to talk about our work on learning gradient fields for shape generation. This is a joint work with Guandao, Hadar, Zikun, Serge, Noah, and Barav. And in this work, we present a novel approach for shape generation from point cloud data. Point clouds is an important 3D representation for modeling shapes, with many applications relying on the recognition, manipulation, and synthesis of point clouds. For example, an autonomous vehicle may need to detect cars in sparse LiDAR point clouds. An augmented reality application may need to scan its environment. Or artists may want to further manipulate scanned objects to create new objects and designs. A generative model for point clouds can create additional training data for recognition, complete scanned objects, or synthesize new ones. Here, we are interested in learning a generative model that maps random noise to shapes represented as point clouds. For simplicity, we start with a 2D shape. We model shapes as a distribution of points, such that points residing on the surface of the shape have high probability, and off-surface points have low probability. You might notice in this figure, the distribution is defined even outside of surface. Later, we will show how to define it. A cloud of points from the shape surface can be thought of as a set of samples from this underlying distribution of points. Prior works have modeled a normalized distribution of points with a float-based network, which is difficult to compute and also results in prohibitively slow training. The other kinds of prior work use implicit representation, such as sign descent field or occupancy, to directly model a watertight shape. However, the ground truth supervision is difficult to obtain only from the point cloud data without corresponding meshes. And also they cannot cope with non-watertight meshes. Our key insight is that we can bypass these challenges by modeling the gradient of the probability. It's not obvious that we can learn it from point cloud data only. We can produce a point cloud by moving points along the gradient field, and this gradient indicates the direction in which the density grows the most. And all we need is to predict the gradient field. Next, I would like to talk about our method. So we use a network to model the gradient of the log density. Given a sample location X, the network predicts the gradient of the log probability distribution at the point of X. Knowing the gradient direction, we can move points towards high likelihood regions, that is, moving the points to the shape surface. Next, we will explain how we learn this gradient field. To set things up, we first know that the true distribution of points is non-zero only on the surface and zero everywhere else. And this makes the distribution discontinuous, so the ground truth gradient is undefined on the surface. Instead of considering the true discontinuous distribution of the points, we approximate it by smoothing it with a Gaussian kernel and model the gradient of this smoothed distribution. The amount of smoothing controls the granularity of information which is captured in distribution. Here, when the amount of smoothing, denoted by sigma, is large, the gradient fields reveal a coarser shape. And when it is small, it can capture more fine-scale details. And we model this gradient field using a deep neural network called G-theta. A simple objective function to train this network is to minimize the L2 loss between the network prediction and the ground truth gradient of the smoothed block density at multiple sampled locations. For example, at a location denoted by X in this 2D case. However, a key question is, how can we compute the ground truth gradient field from a set of point clouds? We follow prior work and compute the ground truth gradient field by perturbing the provided points with Gaussian noise. The approximate ground truth gradient at a perturbed point, denoted as xi tilde here, is defined to be in the direction of the original data point xi. Then we can do a simple L2 loss between the predicted gradient and the approximate ground truth gradient at the point xi tilde. With enough sampling, the network is able to model the true gradient field from the supervision with these approximate ground truth gradients. Note that the gradient field is different for different noise levels. Our framework is conditioned on multiple noise levels to predict different gradient fields. Conditioning on multiple noise level is important. Here, for different noise levels, we show the perturbed points at the top row and the gradient field at the bottom row. On the one hand, we want to supervise the gradient field everywhere, which is hard to achieve with only a small sigma value. And on the other hand, if we want to model a fine-grained structure, it is difficult to achieve with only a large sigma value. And once the training is complete, we can move randomly sampled points to the shape surface using the predicted gradient conditioned on different noise levels. And it is necessary to annul from a large sigma value and gradually reduce the amount of noise. Otherwise, the points cannot be moved to uniformly distribute on the surface. Apart from point cloud, our model can also extract an implicit surface. This is because we know that on-surface points have high probability. And when the sigma is small enough, the log density of the on-surface points is the local maximum. And that means the norm of its gradient should be 0. And intuitively, we can retrieve the surface with a raycasting technique using a 0 gradient condition. Here, we show some results that our model can work on shapes from complicated topology, shapes from non-watertight meshes, and sparse scanned point clouds. Now we know how to model a single shape with our neural gradient field. Then, how can we model shape collections for autoencoding and generation? We use an encoder network, which learns the latent code Z from the point cloud. And the network G-theta is jointly conditioned on this latent code Z and the noise level sigma for learning the gradient field. And we use an L2 loss to optimize the encoder and the network. Up to now, we focus on how we can learn the distribution of points. To generate novel shapes, we also need to learn the distribution of shapes. There are multiple ways we can model the latent code space, and we decided to use a latent GAN. That is, given a random noise, the generator outputs the latent code. And during the training, the discriminator is trying to distinguish it from the real latent code. Finally, I would like to show some results. According to the recent follow-up works, our method is still close to the state of performance on the point cloud autoencoding and generation tasks. And we show that our model is able to extract an implicit surface of the shape. We show some examples of generation results on the airplane, car, and chair categories. Compared with the generation results from Argan, Chigan, and point flow, our generated shapes are visually cleaner. The learned latent space is diverse, which demonstrates that our model is able to construct a reasonable latent space for shape generation. In conclusion, our method models the gradient field of shape, which is a vector field instead of a scalar field. It can be trained only with point cloud data without corresponding meshes, and enable point cloud densification and surface extraction. And our method can model shapes from non-watertight meshes. And it enables fast and uniform sampling of point clouds just by moving points along the gradient, where the gradient fields can represent cost to find shapes with different noise levels. Please check out our code and paper, and feel free to contact us if you have any question. Thank you for your listening.
Thank you, Ruojin, for the great talk. We will proceed to the talk of our headliners and have a joint Q&A session at the end. So now I introduce our headliner, Dr. Lingjie Liu. She's a Lisa Meitner postdoctoral research fellow working with Professor Christian Theobald in the Visual Computing and AI department at the Max Planck Institute for Informatics. She received her PhD degree at the University of Hong Kong in 2019, advised by Professor Wang Wenping. Before starting her PhD, she obtained a bachelor degree in computer science at Huazhong University of Science and Technology in 2014, supervised by Professor Jing Hai. Her research interests include neural scene representation, neural rendering, human performance modeling and capture, and 3D reconstruction. As many of you in the audience might know, incorporating deep learning into the task of reconstruction has been a very popular research topic these days, with many impressive results. And Lingjie has an extensive line of great work in this area, which we are really excited to hear about. Most specifically, she will talk about creating photorealistic animatable human characters from only RGB videos, high quality reconstruction, and the fast novel view synthesis of general static scenes from RGB image inputs, and scene regeneration with the 3D generative model. And now we will let her take it away.
Hi, thank you, Zihan, for the kind introduction. Hi, everyone, I'm Lingjie Liu from Max Planck Institute for Informatics. I'm now sharing my screen. I'm very pleased to share my work with you today. Today, I will talk about the neural representation and the rendering of 3D real-world scenes. We live in a world that is 3D. As shown in this video, our activities such as dancing, playing instruments, and interacting with people and objects are all performed in 3D. We digitize our world in 3D representations. This allows us to visualize the real-world scenes from arbitrary viewpoints. This also helps us better understand the real-world scenes. For example, here to help surgeons observe and make decisions during operations. Furthermore, 3D representations allow us to interact with and edit the real-world scenes at our wills. Also, the future artificial intelligence should have capabilities to understand and interact with the 3D world for better behaving and helping people. Therefore, my long-term vision is to develop AI technologies that can perceive, understand, and interact with the 3D object, people, and the environment. Specifically, my research will pursue 3 goals. My first goal is to achieve production quality reconstruction of real-world scenes from sparse 2D images or videos as input. And given like this reconstruction of real-world scenes, my second goal is to efficiently synthesize photorealistic imagery of the reconstructed scenes, and also allow users to control like the 3D contents for the image synthesis. My next goal is to automatically generate like a large amount of realistic 3D scenes and their corresponding imagery that can be used to train these 3D learning models. Next, I will explain why these goals are challenging. So modeling and rendering real-world scenes are 2 key problems in computer graphics and have been explored for decades. And the classical computer graphics pipeline solved them as 2 separate problems. So first is like you reconstruct the 3D scenes from 2D images, and then you use like a computer graphics rendering to render your reconstructed result. And the automatic way to obtain like the 3D model in the images is to apply some image-based 3D reconstruction methods, such as multi-view stereo and structure from motion. But this method cannot produce a very high quality result. For example, as shown here, like given 100 images as input, the reconstruction result is still noisy and it has a large missing part. On the other hand, like computer graphics rendering methods require very high quality 3D models as input for photorealistic rendering, as shown on the left. And here we show a comparison. We can see like the gap between like the output of image-based reconstruction methods and the required quality of this 3D model for photorealistic rendering. Next, I will introduce my work in modeling and rendering of humans and the general static scenes to address the limitations of classical computer graphics pipeline. And we will start with like human performance modeling. We just mentioned that computer graphics rendering techniques require very high quality 3D geometry and appearance models. But what if like only coarse 3D geometry is available? Like how to use this coarse geometry to achieve photorealistic rendering? For example, like suppose we capture a video around the person, and then we reconstruct like this human model with manual corrections as shown on the right. Then we manually rig this 3D mesh to get the animatable meshes. We can then drive this animatable meshes to move by skinning, and then render these animated meshes using classical rendering techniques. And from this result, you can see this rendering is not photorealistic. First, like you cannot observe some like dynamic wrinkles in this rendering. And also you may observe some skinning artifacts, for example, the bump on the arm. So one way to improve like the rendering quality is to fuse like the classical computer graphics components with generative machine learning models. And in recent years, generative adversary networks or GANs have made greater progress in photorealistic image synthesis. GANs, like trained on a 2D image dataset, can generate like new 2D images that look authentic to human observers. But a limitation of GANs is the lack of explicit 3D control in the image synthesis. For example, it's not possible to change like the camera viewpoint or edit the 3D content in the image synthesis process. So in our work, we propose to combine GANs into the classical human performance modeling pipeline for photorealistic synthesis of human characters under pose control. Specifically, so given like this single view video as input, we first check the body motions in this video, and then we can drive the animated human templates to move. Next, we render these animated meshes in different modalities, such as rendered texture, the depth map, and the segmentation mask. Then we can train a conditional GAN network to translate from these low quality renderings to photorealistic renderings. Once this model has been trained, at the test time, we can modify the body parameters with a body motion from another person or from user interaction. This method is only designed for image synthesis from a single viewpoint. So could I extend it to free view image synthesis? For example, like we have multi-view videos of a person. What would be the result of training the same conditional GAN network on this multi-view data? Here I show the result. So the performance drops significantly. This is due to the fact that our model still optimized in the 2D screen space. So it's oblivious of 3D geometry. One idea to address this issue is to directly optimize like geometry and appearance in 3D. So how to do this? It turns out we can link the reconstruction and the rendering part in the computer graphics pipeline into an end-to-end pipeline by formulating like this image synthesis process as a differentiable physics-based rendering process. In this way, we can compare like the rendered images against ground truth images, and then like the 3D geometry and the appearance can be optimized. And since in this process, the rendered images are enforced to be closer to the ground truth images by minimizing this loss function, these rendered images will be photorealistic. And based on this idea, we propose a new method, real-time deep dynamic characters, or DDC for short, for free view synthesis of human characters with a pose control. Specifically in this work, given like a multi-view video of the person as input, we first like check the body motions in these multi-view videos. Then DDC will predict the geometry deformations in both coarse and fine levels, as well as the texture maps. Then like all these three components will be added to these skinned animated meshes. Then by comparing these rendered images with the ground truth images, these three components can be optimized. Once this human model is trained at the test time, given like arbitrary driving poses as input, DDC can generate like pose-dependent dynamic deformations and appearance in 3D for new poses. One limitation of this approach is it requires a person-specific human template, which means that like for a specific person, you need to like captured a video around this person, and we construct its 3D human template. And also, since meshes have a limited spatial resolution, we can observe like the artifacts on the boundary as shown here. So is there a better 3D human representation that is not person specific, animatable, and has high spatial resolution? The need for being like not person specific and animatable can be met by using simple model, which is a skinned multi-person linear model. But the simple model is very coarse, even without clothes. So it's not suitable for modeling geometry details. On the other hand, recent work proposed neural fields and have demonstrated like high quality results in 3D modeling and the novel view synthesis of static scenes. But these methods are unable to model articulated humans. So in our recent work, New Actor, we proposed to incorporate the articulated coarse model, simple model into neural fields and designed an efficient way to learn this new human representation. We first show a comparison to DC. So with this neural field as a scene representation, these artifacts on the boundary are gone. Before describing our method, we first take a close look to a representative work in neural field, neural radiance field, also called NURF. In NURF, the entire thing is represented as a function that maps a point P on a ray along with a ray direction V to the color and the density at P. And to synthesize the image, NURF will densely sample point on each camera ray and accumulate like the colors and the densities of this sampled points on the ray to produce the color at the corresponding pixel. Next, by evaluating like the L2 losses between the rendered pixel against the ground truth pixel, this neural representation can be optimized. One main limitation of NURF is the slow rendering process. For example, NURF needs 100 seconds to render an image at 2K by 1K resolution. This is because the NURF needs to evaluate a large number of sampled points on the ray using the MLPs. We will discuss how to address this issue later in this talk. So now we know like NURF can model a static scene. So we can use a NURF to represent the scene in a single frame. Next, how to extend NURF to model animatable humans. A naive way is to feed like the body pose parameters, for example, the angles of each joint as a conditioning to NURF. However, using like this pose vector as a conditioning leads to serious distortions as shown on the left. This main cause is that this model treats each frame independently. That is, the network needs to memorize like the full information of the scene in each frame. This is inefficient because we know there are some shared and coherent information across the different frames. For example, like the shape and appearance of the person in each frame would not change too much. Then what should be like an efficient way of encoding all this? So in Neural Actor, we propose the geometry-guided deformable neural fields that aligns like all the frames into a shared canonical space, and then learn the shared space as a neural field. Specifically, like to align this each post space to a shared canonical space, we decompose the full movement from post space to canonical space into two parts. One is the rigid deformation represented by this inverse kinematic transformation. And the other is the post-dependent residual deformations predicted by MLP. And this cannot be modeled by inverse kinematic transformation. With this strategy, a dynamic sequence can easily be encoded and the result gets better. However, this result is still blurry as compared to the ground truth. And what causes like the blurriness? We observe that there are multiple causes, like the complex dynamics of the deforming surface, and also post-tracking errors, and closer body interaction. And as a result, this mapping from the skeletal pose to dynamic geometry and appearance is not a bijection. Therefore, this mapping cannot be learned reliably using a deterministic neural model with the maximum likelihood objectives, such as the proposed deformable neural fields model with L2 loss. And one way to address this issue is to apply adversary loss to prevent the training from converging to the mean value. However, since like the rendering of the neural fields is very slow, calculating this adversary loss on the whole image is infeasible. And to resolve this blurriness issue, we proposed to incorporate a latent variable to break this mapping into two parts. And one is from pose to latent variable, and the other from latent variable to dynamic geometry and appearance. And we only need design the formal parts to handle the uncertainty issue. Then the next question is how to choose the latent variable. As we discussed before, like this variable should ensure that the mapping from latent variable to dynamic geometry and appearance to be a one-to-one mapping. Here we choose to use the texture map as a latent variable, which is aware of a human structure. And there are multifold advantages of using the texture map as a latent variable. First, like during training for each frame, the texture map can be obtained by back projecting the ground truth images to this checked simple mesh. And this ensures like the mapping from the texture map to the dynamic geometry and appearance in the ground truth multi-view images. It's a one-to-one mapping. The second advantage is that this texture map can be used as a local pose representation. That is like for each 3D point P, we can find the nearest surface point. Then we use the textual features at this nearest surface point, which is extracted from this texture map to infer like the 3D deformations and appearance at this point P. And compared to like a global pose vector, this high resolution texture map contains like which information. For example, you can see the wrinkles in this texture map, and which makes like the prediction of 3D deformations and appearance much easier. The third advantage of using like the texture map as a latent variable is that the formal part, this many-to-many mapping from a pose to latent variable can be formulated as an image translation problem that maps this normal map to texture maps. And this image translation problem is well studied in the literature and can efficiently be solved by the state-of-the-art image translation network, such as pix-to-pix or read-to-read. And we can train this image translation network with adversary loss to alleviate the uncertainty issue in this full mapping. Then by incorporating this texture map as a latent variable, this result is crisp and contains the pose-dependent dynamic details you can see in the middle result. And here we show the result of new actor. As we can see, like given like novel poses as the driving poses, a new actor can synthesize the photorealistic animations of the actor with a pose and view dependent dynamic appearance, sharp features, and high fidelity wrinkle patterns. Besides the DDC, we also compared our approach with other 4 state-of-art neural rendering methods. And our method generalized better to new poses and can produce the pose-dependent dynamic details, which cannot be achieved by other methods. Here we show more results. So new actor generalized well to new poses that are very different from those in the training. Here we show a result of challenging dancing performances by new actor from the AIST dataset. These poses are not seen during training. And here we show a free viewpoint video of the person controlled by driving poses. And in this result, like the body parts are well preserved and the dynamic deformations and appearance are properly synthesized. With a new actor, we can apply the same pose sequence to different people to enact synchronized crowd dancing, as shown here. You can observe like the dynamic appearance and the geometry in each of these results. So far, we have discussed like 3 words in human performance modeling. We can summarize the key insight in this problem. First, like differentiable rendering links reconstruction and rendering into an end-to-end optimization framework. And in this way, we can learn like high quality reconstruction from 2D observations, and meanwhile enforce the rendering output to be photorealistic. Second, in this end-to-end optimization framework, how to model articulated humans is a crucial problem. And compared to like classical representations such as polygon meshes, these are hybrid neural representations that combine like explicit articulated human models with the neural fields can achieve like a high spatial resolution for modeling articulated humans. Finally, making full use of these human structure aware features and properties would simplify the problem and facilitate efficient the encoding and generalization. For example, like the use of this texture map as a latent variable efficiently resolve this blurriness issue. Next, I will talk about my work on general static scene modeling. And different from this human performance modeling, where we have like a coarse 3D human model, and here no 3D information is available as input. And our task is similar to before. That is, we intend to learn new 3D representations from 2D posed images, and this learned representation can be rendered from arbitrary viewpoint. As mentioned earlier, a main problem of NeRF is it's a slow rendering process, because like a large amount of sample points in 3D need to go through MLP to infer their colors and densities. But actually, most of these points fall into like the empty space and have no contribution to the ray color as shown in this figure. And here we know that this geometry here is only for visualization, and it's not known in the training process. So how to accelerate the rendering process? Our key idea is to avoid sampling point empty space as much as possible. Therefore, we propose a hybrid representation called neural sparse voxel field, or NSVF for short. The NSVF combines like this neural field with an explicit representation, a sparse voxel octree. Specifically, like instead of modeling the entire 3D scene into a single function as done in NeRF, NSVF defines a set of voxel bounded neural fields to model the local properties in each cell. You can regard like each voxel as a local neural field. And with the NSVF, we can only sample point inside the non-empty voxels here. Thus, this rendering process is more efficient. Besides the efficient rendering, NSVF has two more advantages. So NSVF stores distributed local information in each cell. And this leads to faster convergence of training and also its capability of modeling large-scale things. And the use of this explicit sparse voxels allows us to edit and compose the 3D scenes for image synthesis. Now, you may wonder, if we don't know the geometry, how to build a sparse voxel org-tree. And we learned this NSVF in a progressive way on the fly from course stage to a final stage. And starting from this initial voxels, this sparse voxels will become more and more accurate and compact and converge to the ground truth geometry as the training progresses. And in each stage of NSVF learning, we sample point only in the remaining non-empty voxels, and we calculate the ray color by accumulating the colors and the densities of this sample point. Then we compare the rendered images against the ground truth input images to optimize this scene representation in this stage. And after this stage of training, we will pull on the empty voxels and go on to the next stage, training of NSVF. Here I show a comparison with NERF. Our method achieves both higher quality and faster rendering than NERF. With NSVF, we can control the camera pose and synthesize novel views for a large-scale indoor scene. We can also manipulate the sparse voxels and edit and compose more complex scenes. So far, we have shown that NSVF and NERF can achieve impressive novel view synthesis results. You may be curious about the quality of the extracted surface from the learned representation. Are these surfaces of sufficiently high quality for the purpose of surface reconstruction? And here we show this result. So we can see that these surfaces extracted using marching cubes are quite noisy. And this is because this method uses volume density as a scene representation, which lacks a constraint on surface geometry and thus cannot produce accurate surface reconstruction. Meanwhile, existing neural methods for surface reconstruction, such as IDR, use surface representation, for example, sine distance field or SDF for short, and applying a surface rendering for image synthesis. However, this method easily gets stuck in a local minimum, even with the foreground mask as additional supervision. And this is meaningful because a surface rendering assumes that the ray color only lies in the lies on the ray surface intersection point. So during the training, the gradient would only back propagate to this single point. And in contrast, the NERF is more robust in this case because the in volume rendering will sample multiple points. So the gradient will be back propagated to all these sampled points. But as I mentioned before, NERF is incapable of extracting high quality surfaces due to the lack of the surface constraint in this representation. So in our recent work news, we combine these advantages of these two kinds of method. So we use the surface representation and design a new volume rendering method for accurate and robust multi-view surface reconstruction. But we observe a challenge in this design choice. So first, I show this volume rendering equation, and here C is the ray color, and this W is the color, how much a sample point contributes to the ray color. And the delta indicates where this geometry exists. And in this formulation, simply replacing like this volume density with a function of SDF would introduce some geometry bias in the reconstruction surface. That is like this weight function, this green curve used for like a blending weight in volume rendering does not attain the local maximum at the ray surface intersection point, as shown in this figure. So we propose like a new weight function to address this issue. Due to limited time, I will not describe the method in detail. And here we show a comparison. So News achieves the best reconstruction quality in comparison with the baseline methods. And our method is capable of reconstructing these challenging scene structures from multi-view 2D images. Here are more results of some things from the DTU and the blended MVS dataset. This without demonstrated like the News can reconstruct the complex structures with the self-occlusion and the scene elements. So far, we will talk about how to reconstruct and render 3D things depicted in the input images. Now, let's consider how to generate new 3D things with the corresponding synthesized images. So for this task, a large amount of data is needed to make this model learn how to generate. Then what should be the training data? So it's a multi-view images or single view images. And compared to these multi-view images, single view images are much more easily accessible. And how about the network model? We know like 2D GANs can be trained on 2D single view images and generate the new 2D images. But what 2D GANs generate are merely 2D images without any 3D information. So such model lacks explicit 3D control. Recently, we proposed the StyleNerve, a method that combines like a 3D neural simulations with the 2D generative models. And due to the limited time, I will skip the details, but only show some results. And StyleNerve can be trained on unstructured 2D image dataset. And this trained model can generate the photorealistic, high resolution and multi-view consistent animations of new 3D scenes. And this work addresses the limitations of 2D GANs in generating multi-view consistent images of the same 3D scenes. In general static scene modeling, we have discussed the 3 words. We now summarize the key insights. So first, the hybrid representations that combine like implicit neural fields and explicit representations such as sparse voxel can significantly accelerate the rendering process of neural implicit fields while achieving like high quality rendering. And this and also the use of explicit representation enables like scene editing and composition. Next, incorporating like this surface constraints into the volume rendering frameworks not only ensures like robust learning of neural representations, but also guarantees high quality surface output. Finally, integrating like 3D neural simulations into 2D generative models allows us to generate large-scale 3D things with only 2D single-view images for training. Finally, I'd like to discuss like the future directions. So far, I've been focusing on like a neural modeling and rendering for either static things or humans. And in the future, I'd like to explore like modeling and rendering for things with the interactions between humans and objects. And this will require research on like human object interaction tracking, segmentation, and physics-based simulation, etc. This also requires a data set of human and object interaction for training deep learning models. I'd also like to study the generalization across the person identities. We see like the neural actor and the DDC can synthesize a high quality free viewpoint rendering of a human character on the post control. But this method are not able to generalize to new human characters. So how to extend the existing neural human representations to generalizable models is another important and challenging problem. Another future direction is to synthesize large-scale 3D data for training. So currently, the shortage of like 3D data is a bottleneck for the development of 3D learning. I think one promising way to efficiently acquire more realistic data is by learning like 3D generative models from 2D image data sets. And our work, SciNerve has demonstrated that we can train these 3D generative models on object-centric 2D image data set and use it to generate new videos of new things. But the current model cannot train successfully on more challenging data sets, for example, ImageNet data set, which contains the diverse things. And in the future, I'd like to explore like how to train a 3D generative model on an ImageNet dataset. I'd also like to extend like this neural implementation and rendering techniques to other domains such as robotics. And this neural implementations and rendering method can be used for like 6 DOF estimation, dynamic scene reconstruction and segmentation, and also the prediction of like human object motions. And all of this will facilitate like some important tasks in robotics, like robot grasping, navigation and planning, and human-robot interaction. Finally, I'd like to thank my co-authors. It's my great pleasure to work with them. Thank you.
Thank you both for the great talks. We will now start a joint Q&A session for both speakers. In the meantime, please continue to post questions in the YouTube chat. And if we still have questions left afterwards, please use our Discord channel for offline discussion as well. So first, we'll start with a very general question actually for both of the speakers. So both talks kind of have started by enumerating many different shape representations, such as sign distance fields, point clouds, meshes, etc., but then concluding that the best option to go forward is to consider probability. So Ruojin kind of smoothed the shape into a probability, and the nerve in Lingjie's talk is also a probability distribution. And I think that's because of the application in deep learning, and to some extent, deep learning is all about modeling probabilities. So I guess a very general question is, are probabilities the future's way of representing shapes? So we're curious, what's your thoughts on this?
Maybe I can go first. So I think like this kind of probability, and I think like in the real world, actually the things is kind of in a continuous space. But when we use the sensor to capture it, usually it will be discretized into like point clouds or meshes. But if we have neural network, if we can like reconstruct it back to that probability space and also reconstruct it to the continuous space with this implicit representation, maybe we can obtain like more realistic or high resolution results from it. And also we can, based on it, to have more applications. So that's my understanding.
Thank you, Ruojin, for the answer. What about Lingjie? What's your thoughts on this?
Yeah, actually, I think like for like discrete representations that they have some like limitations because it's not a continuous representation. So you cannot feed like this probability very well. So that is why like recently there is a trend to use the implicit fields as a same representation. But also like we can think about like how to learn these probabilities for discrete representations, but or something like the hybrid representations of the implicit and the explicit representations.
Yeah, that answer makes a lot of sense, and it's a really exciting new directions of research to pursue for future researchers. And we'll start by having some more specific questions for Lingjie's talk. It's really inspiring to see like such a great reconstruction result of deformable humans. We might have missed this in the talk, but mostly we see neural rendering applied to a lot of real world things. And we're wondering what makes neural representation, neural rendering to human characters particularly difficult or interesting as a research problem, in your opinion?
So sorry, it's like use this neural representation and rendering techniques for dynamic or human modeling. It's
yeah, for dynamic.
Challenge.
Yeah, the particular difficulties or interesting aspects of like doing neural rendering and neural representation for dynamic human characters.
Yeah, I think like there are some like multiple challenges in the human modeling using this neural representation and rendering. First is like you need to think about how to efficiently to encode like a large like a long sequence. For example, if you have like a static thing, you only need to encode like the single frame. But if you talk about like humans, the human is moving, so how to efficiently encode like a long sequence, it's like a challenge. And another thing is like how to efficiently model the humans as a articulated representation, because not only like to overfit to a long sequence, but also like how to learn this like animatable template. And this template can use to be driven after like this representation has been learned. And also like in human modeling, we really care about like the pose-dependent dynamic geometry and appearance synthesized. Because for example, like if you have like a static template, you just drive it to move, then you can only see some static textures, and this is not realistic. So how to like synthesize like more realistic wrinkles and depending on the poses of this human. Yes.
Thank you for the answer. And a follow-up question is like, we're wondering, are there like any bottlenecks or difficulties that to extend this to other non-rigid objects that's not human, so like clothes, animals, etc.?
Yeah, these are challenging cases compared to human, because a human you have like a 3D parametric model. For example, this is a simple model. So actually you have a good structure of these human representations, but for other dynamic object, for example, like the clothes and also like the deforming surface, it's hard to like use a template to represent this kind of things. I think this is the main problem.
Yeah, that makes a lot of sense for the difficulty of generalizing to other objects. Now I have a question from YouTube. So one of the audience is wondering, are you able to separate the lighting from the ground truth captures in your data and control it within the neural renderer to have the results you had?
You mean the relighting things? To synthesize some relighting effect. Currently, the method I proposed cannot do this, but we also have like work on the review that we can do this relighting things for general static things. And what we do is that you need to model this like the lighting components in this learning process, and then you can, after like you learn like each component, for example, albedo, specular, and the geometry shading, then you can do like to do relighting effects afterwards.
Thank you so much, Lingjie, for the answers. We're also going to move on to some questions for Ruojin. So we might have missed this, but how are the points uniformly distributed on the surface? So if you just follow the gradients, won't you concentrate the points on the most convex regions of the surface? Have you encountered this problem, or what's your findings?
Yeah, that's a very good question. So actually, like we are doing like a annealing stochastic gradient descent. So that is when we move a point that actually we are moving it based on the gradient from coarse to fine shapes. So that means when it is coarse, it will be moved to more uniform distributed around in a large region of the shape. And then when it is moved step by step, like from annealing from the like coarse shape to the fine shape, and when it is at the fine shape, gradient field actually is almost uniformly surrounded it in a small region. So after the last step with this small gradient, like with this fine scaled gradient, actually it can distribute it finally like on this more uniform distribution on the surface. And also I think I can refer like to more details about how we do this annealing stochastic gradient descent in our paper, like about the algorithm. Yeah.
Yeah, thank you for the detailed explanation. Yeah, maybe people who are curious about can take this offline as well. And another question on the gradients: that if a sample point is far away from the surface where the gradients might be 0, would that cause any issues for the reconstruction from your gradient fields?
That's also a very good question. Like that's the problem that we have confronted like at the early stage of our project. So as you can see, like if the gradient is not defined like far away from the shape, then the gradient will be 0 and we cannot move it. But because here we have a large noise level that we define a coarser shapes gradient field, so that would cover like a larger region around the shape. And also like, so we have some, I think it's kind of assumption that we can sample the points within a uniform, like within like 1 by 1 box like that, because like our original shape is also like the shape is also normalized to this cube. So we can just like initialize the sampled points within this box. I think that's kind of a reasonable and practical assumption for us. Yeah.
So thank you. Maybe last question for Ruojin. Do you have any intuition behind why learning gradient field is better than learning on the raw point cloud locations? On a very high level, I guess.
Yeah, I see. So I think, so if we want to just directly to learn the point cloud's position, I think like we are trying to, I think there's a prior work called like point cloud generation, like point cloud GAN, like that. I think they are trying to directly to model the distribution of each point, but actually that is difficult because compared with that, actually a shapes prior and also the underlying distribution of shapes is not that well captured if we only learn like these separate points like 1 by 1. But here, if we can do it with this gradient field, actually we are trying to understand is underlying distribution of this implicit surface and this like implicit representation, and also and then this way, because we can also do it coarse to fine, and also we can move the points with these gradient fields. Actually, we are trying to make the question a bit easier, and also make the network to have a better like power to predict these gradient fields and capture the underlying distribution. I think that's our intuition.
Thank you for the answer. Yeah, that makes a lot of sense how like gradient field can introduce like a prior to help the learning process in some sense. We are really kind of running over time, so we have to stop here. And so for people with more questions, please feel free to take them offline in our Discord channel. And thank you again for everyone joining our session this week. And so For next week, we have Joshua Walker from University of Pennsylvania and Yifei Li from Massachusetts Institute of Technology. And we look forward to see you again next week. Bye.